Hello everyone, welcome to lecture 6. In this lecture, we're going to talk about the velocity and attenuation in soils, which is the chapter 8 of our textbook. This lecture will cover the section 8.1 to 8.3, and the lecture 7 will cover the rest of the sections. This table shows the wave velocity, density, and the mechanical impedance of different materials. Let's look at the numbers. So air, we know that the sound, the velocity of the sound is about 340 meters per second, right? And it differs with the relative humidity. And the water, it's good to remember, the PA velocity is about 1500 meters per second. And fluids are similar to each other, and salt is much higher, and quartz 6000 meters per second, and calcite, right? And you can see the density is about 2.65 gram per cubic centimeter. And limestone and sandstone, and they vary depending on their porosity. Right, so sandstone 2000 to 5,000, 5,500, and basalt or granite is more than 5,000 meters per second. And soil is a granular salt. When it's dry, it's about 200 meters per second, and the wave velocity of the soil is actually differ, and it varies with its confinement, or the effective confining stress. So it's all under the 100 kilopascal confinement, and clay has the shear velocity of 60 to 150 meters per second. And what else? Ice is much faster than the liquid water. Liquid water is 1500, and now it's 3000. And steel is about 6000, aluminum 6000 meters per second. And when you look at the impedance, like impedance of the metal, like steel, lead, nickel is about like 40 to 50, but the soil is only less than 1. And the rocks also have about like 10 to 20. And fluid, because it's low density, the impedance is less than 3. And when we look at the attenuation, so this is the Q quality factor. So it should be a 1 over 2 times of the damping ratio. And the water it has very high Q. That means that it has low attenuation. And aluminum is also one of the high Q material, so low attenuation material. And the rocks, you see, for the S, P is about 100 to 200, and it differs with with its saturation. And soil is about 8 to 150, and clay is much low Q, so it means the high attenuation. And when we convert it to the damping ratio, so this is about 0.5%, or 0.3 to 0.6% when it's dry sand or saturated sand. And saturated clay has much higher damping ratio, 1 order of magnitude, 1 to 3%. And in this section, we'll see the effect of saturation on P wave. In the velocity and the attenuation, both. In the previous chapter, in chapter 7, we've derived this equation based on the Biot-Gassman equation. Right? And you can see that the bulk modulus of the saturated soil is sum of the skeletal bulk modulus and the fluid part. Right? and the shear modulus is now affected by the its fluid property. And in saturated soil, the PUA velocity is primarily controlled by the bulk modulus of the fluid and porosity. And the bulk modulus of the material then makes the grain BG. So then we can play with this equation and see how this porosity changes the PUA velocity. To do that, we can compare the PUA velocity in saturated condition and normalized with the fluid PUA velocity. So then here, if we replace the BW, the water bulk modulus over the grain bulk modulus with alpha, then the equation becomes this. And impedance also, you can derive the impedance using these two parameters. So then, when we plot to see the effect of porosity on this P wave velocity, normalized P wave velocity with the fluid velocity, when the porosity is 1, which means there's no solid, right? It's whole empty. And when it's 0, then there's no void. So then, no void. You can see that it decreases a little bit, and then it increases as the more grains are filling in. And it starts from 1, and it almost goes to like 2. It becomes double. So here, it's gonna be like 1500 meter per second when it's water. And here we can see it could be around like 3000 meter per second, approximately. And what about the impedance? Mechanical impedance, it starts from 1 and it kind of goes much more than the PUA velocity. So while the normalized PUA velocity initially decreases with porosity, here this part, it's a little bit, there's some reduction, and the normalized impedance remains always above 0.1. And when there's air bubble, so the degree of saturation is now less than 1, then less than 1. For soil with lower degree of saturation, the bulk modulus of the fluid approaches to 0 because of the air. P air is much less than P water. Right? So this is about 2 gigapascal, and this is about 100 kilopascal. Right? So there's a lot difference. Huh? So because of that, as the degree of saturation here is volume fraction of the air, so this is perfectly dry case, so and this is saturated, and it drops exponentially. Right? If we consider this bulk modulus drop, the fluid bulk modulus drop with degree of saturation, air saturation increase, we can also plot the PUA velocity as a function of degree of saturation. And you can imagine it's gonna drop really fast, and this red line is from the equation. And if we assume this Gassman's equation is valid, and PUA velocity drops really fast when there's like 1% of the air volume, in pore 1% of the air saturation. And so it kind of goes to 200, 300, maybe like 300 meter per second, 350 meter per second. And here it's about 1600 meter per second, a little faster than the water velocity. This point shows the experimental results, actually the real test result. And you can see that it also drops really fast, and this axis is the log scale, so it drops really fast following the Gassman's equation. So in 1998, Ishihara and his co-worker also thought the same thing. So based on the Gassman equation, they're gonna develop and verified if the Gassman equation works in soil. And this red line is the theoretical prediction using that equation, and these dots are the experimental measurement. And there are some deviation, but you can see that it shows the same trend with the decrease in B value. So B value is defined as delta U over delta sigma confining. So that means that, for example, sigma naught is maybe like 100 kilopascal in the initial, and you are increasing this sigma naught to 200 kilopascal. So now delta sigma is 100 kilopascal, right? And then what will happen to the U? So if U was 0, and if this pore water pressure inside this specimen increases to 100 kilopascal because of this confining stress increment, then your B value will be 1. Right? If you have only 50 kilopascal increment in pore water pressure, then your B value will be 0. So this B value shows that if the fluid, the soil, are fully saturated with water or not. So again, another data set about the effect of water saturation or B value on the P and S wave velocity. You can see that the S wave velocity doesn't change with the different air saturation, but the P wave velocity drops really fast. And in the left and right, it shows the same trend. Now let's talk about the P wave attenuation and effect of degree of saturation on the P wave attenuation. This is the measured test data with the sandstone, and I can switch. Yeah. When you look at the wave velocity, as the degree of saturation increases, let's start from dry condition. Shear wave velocity decreases with increasing water content or degree of saturation. Why? Because the density increases, right? While the shear stiffness is the same. So shear wave velocity is G over rho. And what about the P? P wave also the same with P E over rho, and density increases with the increasing degree of saturation, but the elastic modulus doesn't increase that much, so it kind of decreases. But as suddenly it just went up really high, up to a certain point here, and that's because of the when it reaches to the full saturation, so air bubble is almost gone. So now the fluid bulk modulus increases to the water bulk modulus. And when you look at the P wave attenuation and S wave attenuation, S wave attenuation is almost the same, and then it just went up as it approached the full saturation. What about the P wave? P wave attenuation increases little by little, gradually, as you added more water, because the water will cause additional friction with the air. But when it approaches to the full saturation, you have decrease. Now that the air phase is almost gone, so that there are not much interface between the air and water. So please read this paper. This paper is kind of Bible, and it's fun to read. So again, it's the same data, similar data, but it shows the spectral response. And when you look at here, you can see that the attenuation, when it's perfectly dry, it's about 30 or 40, and increases gradually 50, 60, 70, 80, and then it peaks at about 80%, and then it kind of decreases again. So as the saturation increases, attenuation increases, and here the local flow and the movement of the droplets and the compression of the gaseous phase attributes to the Q, or the damping ratio increase. As the saturation increases more than 80%, then attenuation starts decreasing. Okay, what about the SOA velocity? When we look at the degree of saturation, effect of degree of saturation on the SOA velocity, we should focus on the capillarity. So, because it's gonna develop some surface tension that increase the confining stress or the contact stress between the grains. So this is the like unsaturated case, right? So you have air and this is water, and because of the surface tension, they hold together better, right, with a greater force. And as it dries, you have more capillarity, right? Higher capillary force developed as the water content goes down, and goes smaller, and then when it's dry, and then it, this capillarity will go and disappear, go away. So then when you look at the clean bead data, when it's fully saturated, it's about 100 meters per second, right? And as you dry, so, and as you dry the soil, as you dry the glass bead pack, it increases a little bit because of the capillarity, right? And then also increases dramatically because of the meniscus developed and surface tension. And you can see that it's almost gone. Now it drops back to about 110 or 120 meters per second, right? Because it's clean. What about here? And it increases, and then it didn't show any drop, right? No drop. Why? That's because of the salt precipitation. So this sand has some salt. So when it dries and it remains this kind of a crystal, salt crystal, right? And it acts as a cementing agent. So it increases the shear stiffness and also increases the velocity. What about this one, kaolinite plus glass bead, and it starts around like 100 meter per second, and it increases gradually, and then it suddenly increases. It went up like this, right? So there's some capillarity. Or capillary effect. And what happens in here? Why have sudden increase at very low degree of saturation? That's because of the clay particle here. The clay particle works as a cementing agent. So up to here, it's because of the surface tension between water and air. And from here, the clay particle bridges the sand particle. It makes the chains and buttress like this. So you can see these are the clay, and clay particle aggregates, right? And this big one is the sand, and this big one is the sand too. And what about the attenuation? I think we've talked about the effect of water saturation on P and S wave attenuation in chapter 7. It's the same. When it's fully saturated, so when the degree of saturation is 100%, then there's no fluid flow, and also there's no air, so there's no compression of the air phase, so the damping is very small, right? And in the case of shear wave, fluid flow is minimal, but it's there, so that it causes the additional energy dissipation. So pure shear wave causes compression in some regions and dilation in others, thereby enhancing the fluid flow. So we've seen this relation before in chapter 7. In unsaturated media, when degree of saturation is less than 100%, high compressibility of the gas and water mixture enhances the fluid flow mechanism in compressional mode, and local flow movement of the droplet. We've seen this one before. And so damping of the P wave is bigger than the damping of the shear wave. Okay, the last section of this lecture is isotropic stress state and the effect of porosity. Stress state, if it's continuum, the minimum effect on the stiffness. So for example, if you have a steel bar, and when you confining it with the like water or something, right, then still the modulus of this material doesn't change that much. But if you have particulate material or granular material made of soil grain or made of maybe rice bean, when you apply confining stress, then the medium E, let me use E and G changes with this stress, right? So stiffness of the skeleton is primarily determined by the state of effective stress. And so the velocity stress relationship for granular matter or granular media, it can be expressed with this relation, right? Alpha times sigma to beta, right? And alpha and beta are experimentally determined. So the general form of the result that you will see in the shear wave and the effective stress relations will look like this. So as the vertical effective stress increases, and shear wave velocity also increases. So you can see a very fast increase in the beginning when the effective stress is low, and as the effective stress level increases and the increment in shear velocity dies off. And this will be the project 2 of for you guys. So then how the beta exponent, so here B is alpha and sigma and beta, right? And how the beta exponent behave or they change with the soil characteristic. First, the contact effect governs the beta exponent, and fabric of the soil governs the beta exponent. Let's go one by one. And when it's over consolidated clay and cemented soil, it's not sensitive to the effective stress. So effective confining stress, or sigma naught, not prime. So the beta exponent is less than 0.15. Normal rounded smooth particle and dense sand, it follows the Hertzian contact. So it's about 0.6 to 0.2. When it's loose sand, then it will show more compressibility. And when it's angular sand, it's not. So before it was like a sphere-to-sphere contact model, but now it could be a cone to contact, a sphere contact model. Cone to, no, not sphere, the flat surface contact model, right? So cone to plane contact, so then it's about 0.25. And when it's soft clay, then it's about 0.3. It's a highly compressible soil because the electrical force or the Coulombian force is now governing. It plays a role here. When the contacts are governed by the purely electrostatic forces, then it's going to be 3/4. So beta increases with more electrical interaction. So as you have more clay minerals in your soil, your beta exponent will increase. So let's look at the contact effect. Here, this experiment was done with the like plastic particle, like very big, 25 millimeter diameter plastic particle, and it kind of arranged in a row like this, and then they increase the force here, or the confining stress applied on this row of particles, and they measure the shear velocity of this soil column. And when the stress is low, and as you increase the stress, the wave velocity increases linearly with the same beta exponent like this. But you cannot say the linearly because it's a log plot, but there is a straight line. But after certain stress, let's say there is a threshold stress, the beta exponent becomes more steeper, bigger. This is the beta, right? The slope is the beta. So when it's a low stress regime, it's elastic contact, and it followed the Hertzian contact model. When it's high stress, exceeding the like plastic stress or the yield stress, then the contact becomes yielded, right? Which means that you have a more contact area, so that beta increases. And when you have a roughness, so here they use the just smooth particle, which shows us the beta of 1/6, and they sandpaper the particle, or they can intentionally make a rust on that. So then beta increase to the 0.22. So please read this paper. This paper is very insightful. And fabric change, different state. Okay, well, we're not gonna talk about this one now, but we can talk about this one in the next lecture, more detail. Fabric change. This is about when you have too much stress release. For example, the particles are all cemented under stress. Right? And when we decrease this stress by unloading it, then this bond will break as they try to dilate. Right? So then as the stress goes down, because of the particle, the bonding breakage, the beta changes to 0.1. And then when we recrystallize it, it kind of becomes the constant fabric. Here. Oh, not here. Recrystallized it, it becomes like this, 0.04. Let's change this one. Yep, okay. Let's look at the alpha parameter. We've derived this equation in chapter 7, and if we just bring it here, and you can see that this one will be the term for the beta, the stress term. So Vs is alpha, sigma, and beta, right? And you can say beta. And the G is rho times Vs square. So then G max will be proportional to Vs square. So then here the 1/3 will be 2 times beta. But let's look at this part. This part will be comparing, it's going to be alpha square. Almost, no? So then you can see the alpha is function of what? Grain modulus, G, and void ratio, and Poisson's ratio of the grain itself, and coordination number, Cn. So alpha is function of void ratio, coordination number, and grain property. That's G, G, and the Poisson's ratio, G. And we can see that effect here. As you have loose soil is here, and when it's dense soil, it goes to here as the soil becomes denser. Right? So the stiffer the particles, the denser the packing, beta decreases and alpha increases. So as the relative density or the dr increases, alpha increases, beta decreases. And the effect of the particle. So here is the steel, which is very stiff, and you have sand, and you have lead knob, right? And which is very smooth, and the clays are also very smooth. So as the particle becomes stiffer, then alpha increases and beta decreases. What about the clay? As the plasticity increases, which means that the Colombian force increases, so that beta goes up, right? And when the aging or preloading, when there's an OCR goes up, over consolidated ratio, and beta decreases. Or if it's cemented, so beta is high in fine-grained soil with clays where double layer effects are more important, and beta is higher for looser soil when it's like loose sandy soil where the interparticle coordination, or the CN or E, increases more readily by stress. And beta is low in soil that has been subjected to diagenesis, cementation, and over-consolidated clay. This is about the effect of mica. Let's see. For a given L mica to sand ratio, here let me explain what the mica looks like. Mica looks like a platy particle like this, and sand will be a very round. So we are mixing these two soils, two different soils with different content, different fraction. So then as the mica content increases, beta increases. And what else? Here too. So as the, like this square is 10%. This one is 10%. And why is that? Because we've seen before, when you look at the Hertzian contact model, yep, here. Cone to plane contact is quarter, 0.25 beta exponent. Right? Hertzian contact is 1/6. Which one's bigger? This one is bigger. Right? So as you have more angular soil, your beta exponent increases. So as you adding more mica is like you're adding more angular soil. So this is also an interesting paper. And so in summary, now we are going to look at the alpha. So far we've seen the effect of different particle characteristic, also soil characteristic on beta exponent. And now we will see the effect of the soil characteristic on the alpha parameters. And we've seen the alpha parameter is affected by the packing density, so void ratio and coordination number, and G, the shear modulus of the grain, and Poisson's ratio of the grain, right? So in coarse grain soil, you can also derive, or the empirically derive the alpha parameter as a function of Poisson, the void ratio. Right? And for the round particle or angular particle. And for the clay, as the confining stress increases, it compresses really high, right? Because the CC compression index is high, the void ratio decreases. So then Fe also proportional to the sigma naught. So higher velocity changes with stress changes in more compressible soil, and higher compressibility, higher exponent beta. As the beta increases, then the alpha decreases. Void ratio are not covered during the unloading, and stiffness during unloading is determined by the maximum past pressure, or the pre-consolidation stress, sigma p prime. And this is something to remember too. So here you can see PLR. PLR is the same with OCR. So as the OCR increases, then the shear velocity increases. And what else? Beta is 0.25 for the medium to stiff kaolinite specimen, but it can go up to 0.5 when soil becomes more plastic, or even to memorialized specimen. Thank you. That's it for the lecture 6.